you're in. Before I get started, how many people don't have a working iClicker yet? All right, so we're going to be raising hands today, all right? And so keep working on getting one, all right, because we are going to need some better. I want to introduce Antidotes, who has joined our team as sort of the point person here. He's in architecture, and I've just met him for the first time. I look forward to working with him, as should all of you. So that if you have questions about, especially about scheduling and routing sorts of issues and clicker issues, come to Andrew, and he will climb up to speed very quickly, as we all desire him. Okay? So thanks a lot for joining us. You're a lifesaver. Today I want to sort of introduce the science part of the Nexus. And this is very much sort of a 40,000-foot overview of the whole problem. If you understood and could round out what I'm going to talk about today, from my perspective, from the scientific perspective, we're done, okay? But the rest of the class, from my lectures, is going to be backfilling what I want to tell you about today. So my purpose here is to talk about all of the Nexus problems in one lecture, and to talk about a solution, like an existence proof, for each of the problems, and so the problems simultaneously. So there's a set of possible solutions for these things, simultaneous solutions, from a scientific and technological perspective, is not empty, all right? And hence, it is false that there is no hope, okay? That's the point. And the thing that you should keep in mind and look for in the lecture is the interactions among the problems and their solutions, the separate Nexus problems. And the message there is that this is really one multifaceted problem, not four loosely connected problems. Okay, so that's the message. All right, so I like to think of you as the crisis generation, and the battle's going to be won or lost on your watch. My generation has already blown it, all right, but it's not lost yet. So I'd like to raise of hands here, and this is just because I want to get a sense of where you are. Based on what you knew coming into the class, how optimistic are you that humanity will solve the climate, food, water, and biodiversity problems? Are you highly optimistic, neutral, pessimistic, very pessimistic? So let's start with highly optimistic. Who's highly optimistic? Anyone? 2 or 3 optimists, good for you. Sunny outlook. Optimistic, simply optimistic. That's 10% or so. Neutral. Pessimistic. Big number of pessimists. Very pessimistic. Okay, so the distribution is skewed towards pessimism, but with some optimists and some very, very, very pessimistic. And I actually think that's pretty realistic. All right, there are a lot of reasons to believe that we'll blow it at some level, but it's also important to understand that when I talk about blowing it, it's not like this is either or. What we'll discover is that the damages that we incur from our actions increase monotonically and at an accelerating rate. So at each point at which you bring one of these problems in, you're averting worse damages than you've ever seen, all right? So that also means that if you have a delay, you incur worse damages than you've seen today. But accelerating damages sort of cut both ways. It always means that it's always valuable to rein it in. So I want to have 4 antidotes to Nexus pessimism here. Some of these are tongue-in-cheek, but they're actually sensible if you think about them deeper. So the first one is a paper by some people called Rockstrom et al. And they wrote this paper on planetary matters. And I don't want to dwell on this, but what they do is they outline all of the different environmental problems. And incidentally, they don't have the food problem here, which they don't have as an environmental problem. They do have water availability and biodiversity and so on. And then they have the outer bound here, which is the planetary boundaries. And the green space is their assessment of the safe operating space for humanity. And without belaboring this, what they come up with is that climate has just punched out of the green. Biodiversity's hanging way out here. That's a serious problem right now. But water, for instance, freshwater use, is still operating safely within the green. And there are a bunch of other problems that we aren't going to be talking about, of course, like stratospheric ozone depletion and that sort of thing. They're really reined in. And so the point is they try to look at the totality of all environmental problems, not just the Nexus problem. And they say, look, there aren't a whole bunch of others that are hanging out there desperate. All right? So the situation can be looked at holistically, the environmental situation, as one that has a mix of time to act and out of bounds. It's not like it's all hopeless. The second question has to do with Fermi's paradox. Does anybody know what Fermi's paradox is? Yeah, what is it?
Isn't a paradox relating to finding life in outer space? That if there were advanced civilizations and we don't know about them, it either means, it's most likely to mean that there's a certain level of civilization that civilization can't reach, whether it be because there's a technological boundary or they just destroy themselves.
Yeah, so what Fermi said was simply, where are all the little green men? All right, so they, we have a universe that's 14 billion years old. The sun didn't form until 5 billion years ago. So there's 9 billion years even before that. We know that life formed on the Earth almost as soon as it cooled. 100 million years later, there was life here. So if life is inevitable, and we now know that there are so many exoplanets, planets aren't unusual, Earth-like planets aren't unusual. Where are all the signals from the intelligent civilizations, which should be statistically, there's been lots and lots of time. There should be super advanced civilizations everywhere. And so that was Fermi's paradox. Now, the solutions are that people propose are actually proposed seriously. Nick Bostrom is a philosopher in England, in the UK, and he thinks just what you said, that the only sensible explanation really, since it looks like life is inevitable, is that somehow intelligence is self-limiting and destroys itself at about the stage where we are. All right, that's the only sensible explanation. And I like to think of it as the sort of Terminator hypothesis, right? That we do something that destroys ourselves. I actually think that's by no means demonstrable. We don't know yet what the waiting time is between fully sentient life capable of inventing a Turing machine or an apparatus like a Turing machine, discovering all discoverable knowledge. What the waiting time is between the formation of life and that. And it may look like evolution is monotonic when it comes to how sort of intelligent and complicated behavior develops. But think of cephalopods, right? The squids and the octopi that are ape smart. And they've been around for 400 million years on the cusp of sentience without progressing and with arms that can manipulate. So why is that, right? It may be that the last stage is really, really hard. I hope so, because I want my grandchildren to survive. But so this is sort of a backhanded, you don't need to worry that much about the Nexus problem because there are lots of worse things out there. The third thing is the three-body problem, and this is just a book recommendation. Right? This isn't actually a serious part of the course. This was a bestseller in China, and it was then started to be translated into the U.S. a couple years ago. When President Obama left office, he recommended this to all Americans to read. So it's really a great read. And it's another solution to the Fermi's paradox, which is not the traditional. And incidentally, it's a trilogy. And the other two have now been translated, and they are smashing, all right? And I've checked them out first of all, I checked them out with all kinds of literary types who just say, oh my God, they're just unbelievable, right? And they've been the best-selling books in China for quite some time. There's social commentary in them. So there's criticism of the social revolution, of the cultural revolution and stuff like that that's embedded in them. It's an interesting window into cultural differences. And there's lots of string theory and stuff in them that I've checked out with our hot dog string theorists, and it's all true. Right? So it's really cool. Right? It's like you could literally be flying along in space, so far as what we know, and all of a sudden pop into a bubble in which there are 4, not 3 dimensions, and you would survive. Isn't that cool? Yeah. All right, now on to the rest of the lecture. So what I'm going to talk about is what happens if your generation does nothing, what it would mean for you all to solve the problem, why a solution is going to take your whole life, and why immediate action is imperative if you're going to make it, and why a solution is going to require the entire surface of the Earth. So that's the outline here. There's a couple of definitions that I want us to get used to. And the important thing about these definitions, I'm going to have very few of these things that you're going to have to memorize, but I want you to commit these to memory, all right? First one is, what's business as usual? A BAU projection simply continues a past trend into the future. We're always going to be talking about solutions as departures from business as usual. A gigaton of carbon is 1 billion metric tons of carbon. A gigaton of CO2 is 1 billion metric tons of CO2, and it's 3 2/3 times a gigaton of carbon, which is simply the ratio of the molecular weights. When you take a carbon atom that weighs 12 units, and you add 2 16s, which is the weight of the oxygen atoms, you end up with a 44, and 44 12ths is 3 2/3. Okay, so CO2 weighs more than carbon. And a part per million in the atmosphere, you may know that we have 400 parts per million in the atmosphere, 1 part per million. And you can remember these in round numbers. It's going to be good enough for the purposes of this course, because you might remember them for your whole life. 1 part per million in the atmosphere is 2 gigatons of carbon, is 8 gigatons of CO2. So just remember 1, 2, and 8. So when somebody's talking about parts per million, that's 2 gigatons of carbon, and that's 8 gigatons of CO2. And it's because the literature and everything and the newspaper uses all these units, and they don't tell you which one, and it can sound crazy because one of them is 8 times the other, right? And so experts get hung up on this all the time. If you remember 1, 2, and 8. Business as usual. This is before even my time, but there's this character named Yogi Berra who was the catcher of the Yankees during their glory age, right after World War II. He said all kinds of crazy things. And one of the things, the quotes that you hear in popular culture still today is the future ain't what it used to be. And it's tough to make predictions, especially about the future. He was always saying nonsensical things that sounded humorous, but somehow true. And that's the problem with business as usual, is that when we talk about business as usual, there's a lot going into a forecast. It's somehow the expected trajectory without action is what has happened in the past. All right? There's a lot loaded into that assumption. So don't take business as usual too seriously. So what happens if we do nothing? I'm going to use a definition of business as usual. And so what it means to solve the problem is some departure from business as usual. Some departure that still entails cost, because we already are paying costs for every one of these problems. All right? So let's start with climate change. So this is a graph of CO2 in the atmosphere through time. It comes from the start of the Mauna Loa record, where they started to, Ralph Keeling started to measure, Dave Keeling rather, started to measure atmospheric CO2 on top of Mauna Loa in 1957. It's now measured all over the world. It's gone up. When this a figure was taken, it was at about 402 parts per million, coming up from a post-ice age value of about 280 to 290. So it's up just over 100 ppm here or so. I checked it today, and I think it's 407.4 today. So we're up another close to 6 ppm above that. And these wiggles here, that's just seasonal wiggles. So what's happening when it goes up, most of the land area is in the northern hemisphere. And so what's happening there is that's fall and then winter. When the plants are asleep, plants eat CO2 for a living, right? Pull it out of the atmosphere and into their plant bodies. And during the fall and the winter, a lot of that is released due to decomposition. All right, so the leaves of the fall are decomposing on the warm days that we have. That drives the CO2 up seasonally, and then when the plants wake up in the northern hemisphere, they gobble up CO2 and drive it down again, and that wiggle then is a seasonal wiggle. Correspondingly, we've had this spike in the temperature record. This starts in 1980. That's last year. Last year was the warmest year ever. The year before that was the warmest year ever before that. The year before that was the warmest year ever before that. This last year wasn't the warmest year ever, but it was the warmest non-El Nino year ever. And so the temperature is spiking up and up and up. A little while ago, it was common for conservative voices, contrarian voices, not conservative voices, contrarian voices to claim that global warming had stalled, but we've got this big spike, yeah.
What is an El Nino year?
Oh, so there's this fantastic long time scale oscillation in the planet that whose origin is in a sense beautiful and mysterious. In that if you take the simple equations that govern fluid flows and implement them at global scale, with the sun beating down on them, the Earth rotating, and the continents where they are. Okay, that's called a climate model. I think that does that. Some simple equation, Navier-Stokes equations, and a little bit of other stuff. And weather emerges, right? Just like the weather, and we use these models to predict the weather. And one of the things that's really interesting is that all of a sudden an oscillation starts spontaneously as a result, as an unexpected and impossible to comprehend, right, with the human mind. You can understand how that it does come from the equations, but you can't understand why. And this oscillation causes an aperiodic, but quasi-periodic, 3 to 7 year oscillation that involves the whole world. But basically, what happens is that in non-El Nino years, called La Nina years, all right? La Nina years, the name actually was coined by a Princeton professor, George Friedlander. He's a marvelous person and one of the people who really worked all of this out. The wind blows very strongly along the equator from Peru towards Southeast Asia. And it pushes all the warm water over towards Southeast Asia. And colder water upwells along the coast of Peru. It's one of the reasons why if you go to Peru, it's always foggy on the coast. And if you go to Bali, you jump in the water, it's like a bathtub, all right? Now, every so often, those winds relax and the warm water comes sloshing back across the Pacific and blasts up the California coast and causes torrential rains and mudslides and all kinds of terrible stuff. And it also changes dramatically what crops you have to plant in Peru. It disrupts rainfall and agriculture in Zimbabwe. It's this worldwide thing, and we oscillate between those two states. And that's called El Nino and La Nina. It's also called ENSO, all right? And so the name you'll often see is its acronym ENSO, all right?
And they're usually warmer. Like El Nino years are usually
Yeah,
warmer.
El Nino years are usually warmer. And also, as we're going to discover, there are years in which the biosphere loses a huge amount of atmospheric CO2, mostly from burning tropical forests associated with warming. Okay? So good question, thank you. Okay, so this is a complicated picture. And it's one that I do want you to assimilate through time. It's going to appear repeatedly. This is from the so-called IPCC reports. It's actually been modified by a group here, the SBC Energy Institute. It's actually an oil services provider. Schlumberger has provided an incredibly valuable handbook that condenses this stuff. So if you're actually looking for some sort of text to understand global warming, that's the best place to go. Far better than the IPCC and everything else out there. These are the so-called IPCC scenarios. There's 1850 and 2100. That's atmospheric CO2 in ppm, parts per million. Remember that it started back in the pre-industrial below 300 parts per million. And then the black line is what happened historically. And then they have 3 different scenarios for the future. Red is close to business as usual. Up until recent years, accelerating fossil fuel use and land use change. Blue, the dark blue down here, is the only one of those 4 that is consistent with the Paris Agreement. Peaking atmospheric CO2 around mid-century when you're middle-aged, and then declining for the rest of your lives, all right? So this graph shows temperature rise. There's 1 degree, 2 degree, 3 degree, 4 degree, 5 degree for the mean surface temperature of the planet. And this is how much fossil carbon we emit. And this is in terms of gigatons of carbon. There are 2 of those units, remember, for each 1 unit of part per million, right? 1, 2, and 8. And this is the amount that we've emitted to date. And so the black line here shows how much carbon we've emitted cumulatively through time. There's 1980, 2000, 2010. And that's how much the planet is warmed. You see, we warmed about 1 degree, and we burned about this much carbon. And if you want to stay below 2 degrees, which is the Paris solution, you can't burn more than that. That's what that thing says. And if you were to do the business as usual red trajectory, you'd climb way out here to 5 degrees of warming and burn a lot of, but not by any means all of, the reserves of fossil fuel. There was way more fossil fuel than we need to really cook the planet. All right? So study that diagram. There's a tremendous amount of information in it, and that's the point. All right? It is decipherable. Study it, and you will figure it out. Okay? So what happens if we warm? 0 degrees, 1 degree, 2 degrees, and so on. There's roughly the times at which we cross these different thresholds for parts per million CO2 in the atmosphere. And these are roughly the warmings that would accompany that, global warmings that would accompany those increases. And the answer is, as far as the science can tell, up here, monsters come from behind the door, right? Monsters come out into the world. And those monsters are deglaciation and loss of our coastal cities. So you lose big continental sheets, mass extinction. Deep sea circulation stops. Anybody ever seen the movie The Day After Tomorrow? Dreadful Kevin Costner movie, like on old TV. Anybody ever seen it? Who's seen The Day After Tomorrow? Fess up! Okay, good. And so it wouldn't happen that way, but it would be bad. We'll talk about what that means later. Tropical famine is a distinct possibility. The tropics can actually get too warm for agriculture. And so these are things that I call tipping points, and that everyone else calls a tipping point. A big nonlinear change that happens sort of all at once. So you lose a continental ice sheet. Once you start losing it, it's really hard to get it back. It all sort of slides in, and then you'll lose your coastal cities, and that sticks. So there is a tipping point that we're actually quite close to. And it's the one that during the Paris Agreement's negotiation led to the adoption of an aspirational target of 1.5 degrees rather than 2 degrees. And this is it. This is an empirical relationship from geologic records between sea level rise from ice loss at equilibrium now, which takes thousands of years to lose all the ice, and temperature. And you'll see that there's this big jump from 2.3 meters of sea level rise to something like 10 that occurs at 1.5 degrees. Now it's important to understand, so this is this big nonlinear change I'm talking about. There's like a threshold in the planet that you don't want to cross. That's called a tipping point. All right? So it's 1.5 degrees. And that actually led to a change in negotiation and the adoption of this 1.5 degree target. So that's kind of interesting, but as we'll see later in the course, it's important to understand that this equilibrium sea level rise is thousands of years out. And if you plotted the sea level rise as a function of temperature, even 1,000 years or 2,000 years hence, it would be a straight line. And I, for one, don't know what the technology of humanity is going to be in 3,000 years. But I guarantee you it's not going to look like today's. We're either going to be gone, or we're going to be, I don't know, downloaded into machines or something. So the solution that I'm going to propose during this course for the climate problem is to adopt and complete and deliver on the goals of the Paris Agreement, which currently says we're going to limit global warming to less than 2 degrees Celsius at equilibrium. The temperature of the planet is never going to rise from the pre-industrial more than 2 degrees Celsius. Now, as we'll see, we're already encountering significant damages at 1 degree of warming. So we're going to get additional damages at 2 degrees warming. But 2 degrees is, in my view, the closest number that sort of still passes the laugh test. We might make it, all right? We could make it with titanic effort. Probably won't be, but we could make it. But we could pretty realistically level off before 3 degrees. And we have increasingly technologies where we might be able to reduce the atmospheric CO2 over time, slowly, back down to 2 degrees, even if we overshot. So that's what I'm going to mean by solving the climate problem. I want to turn now to the biodiversity problem. This graph comes from something called the Millennium Ecosystem Assessment, and it's a process that the UN undertook, I think in 2005. And what is interesting about it is that they got paleontologists to look at the fossil record and to figure out how many species go extinct per unit time, okay? And this is the background number, extinctions per 1,000 species per 1,000 years, all right? And you can see the number is between 1/10 and 1 for different estimates. Those are marine species and those are mammals where the fossil record was good enough. Now, we also have historic records for how many species are going extinct now, say over the last 500 years. And for different groups, those numbers are 100 to 1,000 times background levels. All right, so we have 100 to 1,000 times acceleration in the background level of extinction. And if we try to guess what it's going to be in the future from models with climate change and land use change, the answer that, from many different ways of doing it, you end up with is that you're going to be another acceleration of at least 10-fold and probably 100. All right? And at these levels, you actually get into what we might call a mass extinction. There have been 4 or 5 periods in the Earth's history in the last 500 million years when all of a sudden a large fraction of global species spontaneously went extinct. And these are mostly caused by physical phenomena. Asteroids or comets slamming into the Earth, blowing everything up. But also, large-scale volcanism looks like it can do some of this as well. So there's large-scale geologic events that can do this. This looks like it's an anthropogenic mass extinction, and it works unless we get our act together. Okay, the current 100 to 1,000-fold acceleration is mostly from habitat loss due to agricultural expansion. And in the future, we expect this mostly from climate change. Now, I don't want to belabor this. There's a little thing down here you can't read, but you can read it if you look on Blackboard. It says, you will not be tested on the material in this box. But that doesn't mean as a curious person you shouldn't look at it, all right? And so there's a mechanism here by which I've made a forecast, because there wasn't a decent paper that actually tried to do this. And so the BAU problem is anthropogenic mass extinction. Under business as usual climate change alone, but with no further habitat loss due to agricultural expansion, you expect, on average, about 1/3 of global species to go extinct. All right, you can read about the methods down here. And that's a reasonable number. You can get that number from a bunch of different angles. If you got the agricultural expansion of about 1.6 billion hectares, a doubling of current agricultural land, necessary to meet, as we'll see in a minute, a doubling of food demand, you'd lose about 60% of species. So these are big numbers, and if the two happen together, you really got a mass extinction on your hands, right? If you institute the Paris solution and don't expand agriculture, it turns out there is an expected 11% of species lost anyway. So 11% of species lost stinks, frankly, right? But it's not as bad as these numbers. So that's what I mean by solving the problem, is only having 11% of the species go extinct. And it's important to take on board here that climate change is exacerbating the species diversity problem. So that's one interaction between these two problems. So the food problem. So I already showed this diagram last time. And what we have here is food demand expected to double by mid-century, primarily because of changes in diet, primarily because of increased protein content of diets as people become more and more wealthy. So that's the problem. How are we going to supply all this food demand? And as I just showed you, if you double cropland to meet the double food demand, what you end up with is a mass extinction. You lose 60% of species on the planet. That's not so good. It also turns out that deforesting the tropics to make farmland has terrible implications for the climate. Turns out that a hectare, that's the metric unit for area, roughly 2.25 acres, 2.4 acres of land is a hectare. It's 100 by 100 meters. Okay, so it's simply to remember, 100 by 100 meters. So it's a football field on the side, right? Square. Each area of that size in a tropical rainforest stores on average 200 tons of carbon atoms in the bodies of trees, which are primarily, the wood is primarily made of carbon. And it would be 4 times that if those trees decomposed and went into the atmosphere. Like if you cut them down and burned them to make agricultural land, or cut them down and stacked them so that they decomposed and went to the atmosphere, it's 800 tons of carbon for each hectare that you deforest. And so if you did 1.6 billion hectares, it's 8 times 1.6 billion. It's like a huge emission, all right? So meeting food demand by expanding agriculture both causes a mass extinction and significantly exacerbates the climate problem. So this is another interaction. Now, beyond that, climate change is going to make the food problem worse. This graph is busy, but it has the virtue of including all the data and projections that's known. The vertical axis, you want to take a look at this. You want to, so this is yield change, percent. That's 0, goes up to 100%, doubling in yield, or 80% loss of yield. This is temperature change locally, 1, 2, 3, 4, 5 degrees. These are actually data. The orange ones are the ones I want you to look at. That's existing crops and studies all over the world. And what it shows is that on average, there are some crops that do better when it gets warmer. These that are above the line here that get increases in yield. But the vast majority of crops in the vast majority of places when it gets warmer actually lose yield and lose a lot of yield, all right? So the situation is complicated, but on balance our crops do worse when we heat them up. And with adaptation, this is if we took the right sort of action, if there were systematic changes in crops, we could do a lot better. The blue line is with adaptation, moving the crops around, and we come close to crossing the line here. So my point is simply that climate has the potential to make agriculture less yielding, and it happens kind of all at once, like when a drought shows up. And so it takes a while for humanity to adapt. And it turns out that, we'll see in a minute what happens when we haven't adapted in time. Now, we're going to be talking about a solution. There are several proposed solutions to the food problem. The best one is by a guy who is now the head of the California Academy of Sciences. If you live on the West Coast and wander around in Golden Gate Park, he's inside that building there. And it simply says, no new farmland or pasture, a 58 increase by closing existing yield gaps, inefficient agriculture that we already have. The rest from increased cropping efficiency, business as usual increases in yields from crop breeding and genetic manipulation, which we've been doing for centuries. Reducing waste, we waste a huge amount of food, we don't have to, and extremely modest diet shifts. It turns out diets are actually hard to change. So this is a very pragmatic solution, and there are several like this, right? It's possible to actually meet food demand without creating a mass extinction. The water problem is interesting because unlike these problems, it's not properly right now a global problem in the absence of extreme climate change. So humanity currently consumes 4,500 gigatons of water, billion metric tons of water. But actually, but the annual supply globally is almost 10 times that. So the idea that globally we're running out of fresh water is just not true. All right, we're using something like 10% or 15% of our global freshwater supply. But the problem is that it's not where we want it to be. It's very difficult to take water from the Mackenzie River in Canada, almost none of which is used, and move it to, Kenya, right, or someplace, right? You just can't move water around easily on the planet. It's so heavy, right? And so the problem is that water shortages are and will remain regional. But climate change is going to worsen water shortages. This is a graph of changes in near-surface soil moisture. So when the near-surface soil moisture becomes red in these maps, it means that you've got drought in agricultural lands because the soil is drier. And when it becomes blue on these graphs, on these maps, then the soil is actually wetter and there's more water for agriculture. And these are the different Ipcc scenarios. Remember, this is the one, 2.6 is the one consistent with the Paris Agreement. Atmospheric CO2 rising to mid-century and then slowly falling. And you can see if we do that, we still encounter significant changes from climate change in water available to agriculture. We're big regions of the United States, for instance, the Southwest here, big portions of Ohio, and that's Kentucky and Tennessee and that sort of thing. The whole Amazon, big portions of Africa, almost all of Europe. It's actually drier for agriculture, which is bad, right? And that's with solving the climate problem. But on the other hand, if we went to RCP 8.5, we've got real trouble, right? In the large regions of the crop producing world, so that this is just an indication that the water problem, the food problem, and the climate problem are all intertwined with one another, right? All the same problem. Finally, I'm going to talk for a whole lecture about the link between sudden shortages of primarily water, food availability, food prices, and violence, warfare. There's an emerging branch of economics that has established extremely tight causal connections among these things. And this is the graph from the first paper on this, which only came out in 2012. This is brand new. These characters assembled a database of 6,000 past conflicts, both revolts within states where you try to depose the leader, civil wars, or between state conflicts, and looked at them in the context of weather that was happening, climate shocks, and agricultural production, that sort of thing. And the first thing they discovered was in the Sub-Saharan African database, which alone has over 6,000 in it. This is the zero here means average rainfall occurred. Out here, it means this is a 1 in 1,000 year wet year, and this is a 1 in 1,000 year dry year. And the line is a statistical fit to the data, and they were just shocked. When the weather gets weird, people start to flight. This is the percent increase from the mean conflict. So these numbers here are 100%. Conflict doubled as a result of either unusually wet or unusually dry years. Subsequently, there's been a huge amount of work done on this, and we'll talk about it. But there is very, very strong evidence that all kinds of conflicts that we face today, all kinds of violence, including the Syrian civil war, are in fact caused by, or at least triggered by, climate shocks. We'll talk a lot about it.
Question.
Oh, yeah.
An unusually wet year would mean that it's like the monsoon season that's destroying, crops or villages. Is that
Yeah, so there are all kinds of hypotheses for that. That initial graph hasn't really held up as well. What is clear is that on the dry end, things happen, right? So that, for example, the Syrian civil war occurred in the aftermath of the largest drought in history, which in Syria goes back to the third millennium before the current era, right? So 5,000 years ago. And the previous worst drought was in something like 2100 BC. And the worst drought was the one that occurred right at the advent of the Syrian civil war. It drove 500,000 people, made I think 800,000 people food insecure. farmers all moved into the cities and, it started the cycle. Okay, so solution to the water problem. In many ways, this is, although politically difficult to accomplish, it's one that gives me some hope. And it's because we have examples in relatively arid regions in which the water problem is now managed well. Turns out most water is used to irrigate agriculture. And the biggest problem is that the historical way of managing this, if it's managed at all, is by giving people hereditary water rights that go with the land. And so you don't have any incentive to save. Whatever water you own, you spend, right? You gotta hold them to do it. And instead, if you create a marketplace for water, all right, give each landowner a water entitlement, a set fraction of the stream or groundwater, with the ability to sell unused water. All of a sudden, it gives you a second income stream by conserving water. You can sell some of your water to somebody else. And it turns out this simple mechanism is capable of reducing water use by several-fold. This really works. It's worked again and again and again and again. It's politically difficult to enact, but when you enact it, it works. All right? So that's kind of good news. Okay, so why would a solution to this problem, why is it going to take you your whole lives? Why can't we just get done with it? Why can't my generation just kind of finish it off and leave you in peace? Right? Well, the first problem is that there are many sources of inertia in these problems. And arguably the most important is that the infrastructure that needs to be replaced for the climate problem is long-lived. A coal electricity plant lasts 40 years, and there are lots of new ones all over the world, particularly in China and increasingly in other parts of the developing world. Pipelines that you put in place last 100 years, all right? Dams and canals for irrigation last centuries. There are canals in operation today moving irrigation water that were made millennia ago. All right, so the infrastructure is just long-lived. The second is that the climate lags the atmospheric CO2 by a lot, and it's because the atmosphere slowly has to heat up the oceans. We'll talk more about that. That takes a long time. This is a graph from climate modeling that shows what happens if you were to snap your fingers and instantaneously double the atmospheric CO2, and then keep it constant at that level. And what would happen is that 66%, 2/3 of the warming would happen in about 100 years, and the rest of it would take another 1900. All right? And this is the slow warm-up of the oceans. And so, although the atmosphere has warmed 1 degree already, from the atmospheric CO2 we've pumped into it, that's only about 2/3 of what we're going to get, even if we froze atmospheric CO2 at the current level. The atmosphere of the planet's still going to warm for a long time, albeit slowly. It's the second reason. There's inertia in the climate system. All right, and the third reason is that human attitudes change slowly. And the reason for the course is that I'm banking on generational change. Right, frankly. I've always thought that I got in trouble last year because I called this a myth. Somebody objected. The religious tradition of Moses spending 40 years in the Sinai wandering around. If you've ever been to the Sinai, it's not very big. It would be hard to wander around the Sinai lost for 40 years, right? I mean, all you got to do is like walk straight in a row for like 3 days and you're out of the Sinai. You spend 40 years wandering around the Sinai, go figure. And I don't know what he's doing there, but the answer was he was waiting for a generation to die. The slave generation had to die. I think that's the purpose of the religious tradition, is that sometimes the change needs to be generational, right? All right, so you got to wait for us to die to solve the problems. All right, so why is immediate action imperative if humanity is to solve the problem? Well, the answer is, we're actually getting close to some sort of dangerous points, right? I already said that the temperature we've got today is actually quite close to the tipping point on that graph. It's starting to flirt with sort of nonlinear danger points. The second is that for some of these problems, like the biodiversity problems, a large fraction of the species are already at risk. It's not like 1 or 2. So this is the fraction of mammal species that are endangered, and it's a quarter. All right, it's a large fraction of species that are already endangered out there. Amphibians, it's something like a third, and so on. So there are a lot of. I mean, this is underway. It's not like it's just getting going. Kofi Annan has the only estimate I know. He's a previous Secretary General of the UN. He has a foundation, and they try to estimate current impacts of global warming, extreme weather primarily produced by global warming, on how many people a year it kills. And he came up with currently today over 300,000. Now, I've got to be honest, I have absolutely no faith at all in that estimate. It's the only one that's out there. And I actually think it's an interesting challenge to come up with an estimate like that. But the estimate is at least credible. The number doesn't raise my hackles. It's just that I don't think the method is particularly sound. But still, 300,000 is a big number. That's the kind of number I expect when it's done right, something in the hundreds of thousands. And you have to remember that that happens every decade. There are millions a decade that die at that level. And so you get numbers like World War style numbers over time from this. So these are events already, probably, they're of the scale of global conflicts in terms of how many people get killed. He also estimates $125 billion of damages. We can talk about all of this later. I'm suspicious of all of these numbers. It's also known that food shortages kill a lot of people, right? 3.2 million deaths of children under 5 and 800 million people malnourished. Those numbers are a lot more believable. But those are also getting better, incidentally. Extreme poverty is being reduced through time, not increasing. It's being reduced rapidly. So accelerating damages are probably already among us, and certainly the climate damages are demonstrably accelerating, as you'll see in the course. So finally, why does a solution have to take the whole surface of the Earth? All right? And the simple answer is we need all of our existing land, agricultural land, to feed humans, even if we do everything that we know how to do. All right? And already our biodiversity is collapsing, given the habitat expansion of agriculture to date. All right, and so collapsing it further is really unlikely. So that, for instance, raising gigantic amounts of energy-producing crops for biofuels to address the climate problem is going to come from one of those two big pools, and either greatly exacerbate food shocks and cause violence and cause all kinds of trouble, or it's going to take tropical rainforest and induce a mass extinction. And so we're kind of hemmed in. In some real sense, it's worth thinking of every square meter of land as already used for something. It preserves remaining biodiversity, it produces food, it produces fiber that we use for wood products and that sort of thing. And so on. This is E.O. Wilson, who's a famous sort of Harvard ecologist, I guess, conservation biologist. He wrote a book called Half Earth, in which he makes the case, and it's a reasoned case, that if we were really sensible stewards of the Earth, we'd put half of it in a preserve. About half of it would be enough. Right? And this is a title of an archaic James Bond movie called The World Is Not Enough. So that's the problem is currently the world isn't enough to solve these problems, right? And that's it. So these are the things, I should say, these are teaching goals. You should read these. And the way to review this lecture is to go home, take a look at those teaching goals, take a look at the first one, and go through the lecture and say, can I do this for anything relevant? And go through each goal that way. If you can do that, if you're able to do that in your mind eventually, you will ace all of these exams. If you can't do it, masa, right? Not so good. But there won't be any part of the exams that does not have one of those two goals, right? So there's nothing on the exam that isn't